Okay, so this is your lecture video for chapter 3. We'll start talking about momentum and then conservation of momentum, and then we'll talk about energy. Sorry, and then we'll talk about forces. So Newtonian laws of motion. Okay, so first things first, let me just tell you the learning outcome. We need to know and we need to define what is momentum and what is impulse, and then we'll need to work with that. So, for example, I'll do example problems in our face-to-face session, and then of course we need to look at the FT graph, so force times time graph, right? So let's begin by looking at the motivation behind momentum. So let's consider a ball of mass m. Obviously, the mass is not zero, but the velocity of this ball is zero. It's not moving. When it's not moving, we call it static. So the mass content or the matter content of this ball is just what we call mass, right? Matter content. Now consider another ball, right? But this ball has the same mass as before. It's not zero, but this one is moving at some velocity, right? So now our velocity is no longer zero. In order to differentiate between these two, we introduce a new quantity, right? We introduce a new quantity, and that quantity is what we call momentum. The most common symbol for momentum is P, okay? And we define this quantity as being just the product between mass and velocity, the mass of the object and the velocity of the object. Now, velocity is a vector quantity. Therefore, you have a scalar multiplying a vector. Therefore, the product is going to be a vector as well. It's particularly important for you to know the direction of momentum because, after all, it is a vector quantity. So let me just cover a few things before that. I want to clarify that mass has the unit of kilogram, SI units of kilogram, and then velocity has m as -1. So we know that if we want it to be homogeneous, we will have to have momentum to have units of kg, m as -1. Okay. Okay. So we've defined momentum. Now the question is, what happens if that momentum change, right? If that momentum changes, that means delta P is not equal to 0, right? And our delta P in general is simply going to be mv minus mu, okay? Of course, if you're talking about the same object with no loss in mass, I can take it out, right? I can have v minus u. Right? So this change, if it's not 0, we can call it as impulse. Okay? This change in momentum is what we call impulse. Right? So just remember that impulse is just the change in momentum. Not with time, just the change of momentum. Okay? The interesting thing about this is that when we look at Newton's second law, which you have covered in SPM, but I'll remind you a bit of it here. F equals to ma, and then a is just m dv dt, right? M dv dt, and this is simply mv minus u over some period of time, right? We can see that mv minus u, this one is just momentum. Sorry, no, impulse is just impulse. Therefore, what we can say is that our force is actually our impulse over time, or at least over some time interval. This gives us a clue on our FT graph. Okay, whenever you have a graph, you always look at two things. You look at its gradient and you look at its area under the graph. Now, if I were to just rearrange this equation, I'll have J equals to F times delta T. Now, this is so impulse is just a product of f and delta t. So if I were to just take some value of delta t, and then I shade that, shade the area under the graph, that is just the impulse. Okay, so the area under the graph represents impulse. Okay, that is all from me for this video, for this part of the video. Thank you very much. Okay, good day everyone. Welcome to the second part of the video. In the first part of the video, I've talked about the definition of momentum. I've defined what is impulse, and then I've looked at where impulse fit into the FT graph. In this part of the video, I want to talk about conservation of momentum. So let's get into it. Conservation of momentum is a very important concept. Its statement is simply that if no external force is applied to a system, then the total momentum, will not change. Okay, and when I say total momentum, what I mean by that is simply the total momentum of the system at its final stage minus the total momentum of the system in its initial stage. Okay, so the minus comes from the delta. Summation just means, well, summation. You add up all the momentum. Now, I'm sure you're familiar with this, right? I'm sure you're familiar with this. Let's say you have two interacting bodies. So let's work with one-dimensional cases. If you have two interacting bodies, then the momentum before, so m1u1 plus m2u2 should be equal to m1v1 plus m2u v2. Okay. So the summation of all the momentum, of all the momenta, right? Momenta before pi initial must be equal to the summation of all the momenta in its final stage. Okay. So so what makes it interesting compared to the first the SPM syllabus? Well, you will have to be able to do it not just in 2D, not just in 1D, but also in 2D. Okay, so what that means is that you will have to be able to resolve the velocities in its x and y component. Okay, so what that simply means is that if I have two interacting bodies, so let's say you have two interacting bodies, okay, I have to split their velocities into x and y components. Okay, so in the handout that I have given you, you should find a table which says x component and y component. Okay, and you will have to apply conservation of momentum to x and y components individually. So what that means is that if I have two interacting bodies, I will have m1 u1x, so the velocity, the initial velocity of body 1 in the x direction, plus m2 u2x, right, which is going to be equal to m1 v1x, and then plus m1 v2, m2 v2x. Okay, same goes for the y component. I will have m1 u1y plus m2 u2y, and then you have equal to m1 v1y plus m2 v2y. This is just breaking them up into their individual components. Okay, if you were to combine them, so let's say you want to know its final velocity, So for example, if you want to know its final velocity, you will have to use Pythagoras theorem, where it says the momentum, the resultant momentum, is simply going to be its momentum in x squared plus its momentum in y squared and then square rooted. So this is just a Pythagoras relationship. And of course, when we have that, because momentum is a vector quantity, we need to know its direction as well. So then for its direction, we generally will have tangent theta equals to py over px. Okay, then we can find what's the angle. It's useful, it's really useful for us to just draw it out, okay, so that we know which angle we can use. Okay, now just to wrap up on momentum generally we will apply before and after collisions. However, there are two main types of collisions that you need to know. Okay, there are two main types of collision, which are elastic and inelastic. Okay, so for elastic collisions, okay, we have a loss of energy. In other words, its kinetic energy is conserved. So there's no loss in energy. Okay, all of the kinetic energy remains as kinetic energy for elastic collision. So if you add up all of the kinetic energy before, it will be equal to all of the kinetic energy summed up after. Okay, for inelastic, we have the opposite case. We do not have conservation of kinetic energy. Okay, we do not have conservation of kinetic energy. In other words, when you add up all of the initial kinetic energies of the body, and then you add up all of the kinetic energies of the bodies after the collision, there will not be the same value. Okay, of course, in both cases, momentum is conserved. In both cases, momentum is conserved. Okay. Okay, in both cases, momentum is conserved in any collision. Okay, that is all for this part of the video. Thank you very much. Okay, we are entering the third part of this video, and this third part is, we're no longer talking about momentum and impulse. All right, we'll be looking at forces. So basic of forces. What forces do we need to consider in Newtonian dynamics? Okay, and then we want to learn to sketch a free body diagram. Okay, and then we want to talk about types of frictional force, and then we want to talk about Newton's laws of motion. Now, Newton's law of motion, I'll just mention the statements. The calculation can come on when we have a face-to-face session. Okay, so what are the four forces that we need to consider? The first of the forces is gravitational force. Okay. In SPM, you might call it weight, but it's the same thing. So you still use the same symbol, which is W, and the same equation, W equals to mg. Again, G is directed towards the gravitational source, therefore weight will, so direction will be towards gravitational source. So if your gravitational force source. So if your gravitational source is under you, then the direction is going to be downwards, right? So I'm just going to draw, imagine there's a box hanging in the air for some reason, then your force will be downwards. Okay. Now we look at the second type of force we want to consider, which is going to be tensional force. Tensional force. Okay. This tension force is just a value. It's just going to be a value. But the most important characteristic about it, so the source or characteristic is that it's going to be along the string or cable, the string. one of the words that is generally used is going to be one-dimensional element. One-dimensional element simply means a line. So if anything that looks like a line, it can apply tensional force to it if it's taut, T-A-U-T, taut, right? So if I just have that box again hanging from a ceiling, right? Then tensional force is just going to be away from the body and along the string. Okay, so T is going to be upwards in this particular case. So the direction of tensional force is going to be away from the body and along the string. Okay. Now, the third type of force we will consider. Okay, consider is just a normal force. Normal force. Now, it's called normal force because it is normal to the surface. So this is the surface. This is your body. I mean, not your body, but a body. And then the normal force is going to be directed 90 degrees from that surface. Okay, 90 degrees. It forms as a form of support. Okay, it's normal. Okay. Now, the fourth type of force that you will have to consider is going to be frictional force. Okay, now frictional force, its direction, its direction is going to depend on the direction of the body. So if the body is moving to the right, then frictional force is going to be to the left. Okay, if the body is moving to the left, then its frictional force is going to go to the right. Okay, that's all it is. Okay. However, what if the body is leaving the table? So if the body is leaving the table, do you have frictional force in the opposite direction? No. And the simple reason is, in order for you to have frictional force, the body and the surface, so body and surface, must be in contact. If the body is, up here, it is no longer in contact. Okay, so it has to be in contact with some surface, and then it's going to be directed in the opposite direction of the motion. Okay, now for frictional force, we have two types of frictional force. So frictional force, two types. The first one would be static. The second one would be kinetic. Static simply means that the body is not moving, or at least the body wants to move, but the frictional force is stopping it from moving. And kinetic is when the body is moving. Okay, moving. In general, your static friction will be bigger than your kinetic frictional force. Okay, and for frictional force, in general, we will have mu n as its equation, n being normal force. So this is normal force. So if I'm talking about static friction, I will have written there static, and then this is what we call the coefficient of static friction. Static. Okay, and then if I have kinetic, which is moving, right, I will again have mu, but this time change the label to kinetic n. Okay, in general, you will have mu static to be bigger than mu kinetic. Okay. Okay, good. So now, last but not least, I want to have a quick mention of Newton's laws. The first one being, of course, if there are no external force, then there is no change in velocity. Okay, so if the thing is initially not moving, then it's not going to move at all. Okay, if it was moving, it's not going to change its velocity. The second Newton's law is going to be F is directly proportional to dp, over dt, which is just the rate of change of momentum. Okay, so the last of the three Newton's law is going to be an equal and opposite. So I'm just going to say, okay, if I have two bodies interacting, the force of body 1 on 2 is going to be equal to the force by 2 on 1, but opposite. So the negative here tells you it's going to be opposite in direction. But because there's no other factors, they are equal in magnitude. Okay? Okay, that is all from me for this whole video. This is the last part of chapter 3. I'll see you in chapter 4. Thank you very much.